My name is Tom. Let's talk about applications of linear algebra, second-order linear homogeneous differential equations in physics. This video is brought to you by myself, Santiago and Rashad. Let's define second-order linear homogeneous equations, illustrate an intersection between the study of diffie-q and linear algebra, and describe applications of linear algebra diffie-q in physics. A second-order linear differential equation is of this form, where g1, g0, y, and f are all functions of a free variable x with a common domain, say negative infinity to infinity. If f over there on the right-hand side is 0, then the equation's homogeneous. A function z is a solution of the differential equation if the equation is satisfied when z and its first two derivatives are substituted into the equation. The general solution is of one of the following three forms. Let's spend some time with the third form at the bottom. The version of the differential equation with the general solution that we just mentioned has a set of specific solutions presented here. What's unique about this set of specific solutions is that the general solution is a linear combination of these two specific solutions. This set of specific solutions is also linearly independent. The only way to enforce the relation that you see here is to set the scaling parameters equal to 0. Moving on to some applications. Let's consider a pendulum. The pendulum is rigid. It has length L and mass m concentrated at the center of the pendulum bob. The pendulum is attached to a pivot that's translationally fixed. The pivot can't move left to right, up or down, front to back. Neither the pivot nor the pendulum experiences forces resisting its rotation. Friction. Air friction, mechanical friction. The pendulum has been rotated away from vertical and experiences acceleration due to gravity with magnitude equal to the standard acceleration due to gravity of 9.81 meters per second squared, or newtons per kilogram. For small angles of theta, such that the sine of theta is approximately equal to that angle theta, the angle that the pendulum makes with vertical can be modeled using this second-order linear homogeneous differential equation. The derivation of this diffie-q involves the force diagram over on the left and consideration of circular motion. The solution of the differential equation modeling the angle of the pendulum is here, and it has that third form that we talked about. So here's a proof that the general solution on the previous slide actually satisfies the differential equation. Feel free to stop and read. Considering the components of the general solution that are combined to form the general solution in a linear combination, those components are themselves solutions of our differential equation. And those components are linearly independent. Here's a proof that our set is a set of solutions of the differential equation, and that our set is linearly independent. This slide is a reference to the pendulum study, which we found in Ron Larson's Linear Algebra textbook, the section Applications of Vector Spaces. Ron Larson suggests that the general solution of the differential equation modeling the angle theta of the pendulum can be written in this form that is a composition of two sinusoidal functions. I'm going to argue that we can't write the general solution of the diff-EQ in this form involving the composition of two trig functions. Feel free to stop and consider the proof. However, I think Ron Larson was moving toward considering whether we could condense the general solution of the differential equation modeling the angle into an elegant, compact, simpler form. And in fact, we can. Here is a proof that simplifies the general solution into a function involving one trig function. This proof involves some neat definitions of parameters and considering geometry and considering trig identities in clever ways. Another application. Here is a schematic of an RLC series bandpass filter. R for resistor, L for inductor, C for capacitor. If we remove whatever input voltage source exists on the input terminals, and we short the input terminals and close the circuit, then the current in the circuit can be modeled using the second order linear homogeneous differential equation that you see on the right. So bandpass filters are pretty important. They're used for AM and FM radio, for example. I'm actually thinking of simulating a large array of bandpass filters for the purpose of processing audio or music. If I pass in an audio or music stream to each bandpass filter in a large array of bandpass filters, then I can detect whether the audio or music signal involves a composition of specific frequencies or specific pitches. And then I can, through my simulation, detect pitches in audio or music. Considering another application of second order differential equations, a solar system model. This is pretty awesome. So this solar system model involves the Sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto, and a fictitious black hole. I believe that the black hole is present to really anchor the positions of the celestial bodies in this model around a central, relatively static reference point. So, having a static reference point and introducing a black hole is definitely a limitation of the model. One more limitation is that we're considering classical mechanics at work here. We're not considering special relativity or general relativity. But let's actually consider the classical mechanics here. What's that big equation actually saying? So, the vector Fi is the net vector force on the ith celestial body. Let's consider Neptune, which is the outermost dark blue orbiting body. So I references Neptune. So the net vector force on Neptune equals, by Newton's second law of motion, the mass of Neptune times the vector acceleration of Neptune. And the vector acceleration of Neptune is the second derivative of the vector position of Neptune. So, what is the net force on Neptune? Well, the net force on Neptune is the sum of the forces on Neptune by all of the other celestial bodies in our model. So we're summing from j equals 1, the first index of a body, up to the last index of a body. And we're not considering the force of Neptune on itself. So again, the net force on Neptune is the sum of all of the forces on Neptune by other bodies. And so let's consider one of the forces on Neptune by another body, J. So by Newton's law of gravitation, this force on Neptune by another body, J, is equal to this product over here on the far right. And that is the gravitational constant G, which is about 6.67 times 10 to the negative 11th in value. And then we have the mass of Neptune, we have the mass of the other body J, all over the distance between Neptune and that other body, cubed. And since we're trying to find a vector force between Neptune and another body, we multiply that quantity on the right by the vector difference in position between Neptune and that other body. If we were just considering magnitudes, then the magnitude of the force on Neptune by another body would be gmm over r squared, which is an early introduction to Newton's law of gravitation. But here we are considering the vector force. Just a note on how to go about solving this. Well, the modeler seemed to consider x, y, and z as a reference frame. And so we could start by breaking down the net force on Neptune into the net force in the x direction, the y direction, and the z direction. And another clever technique to use in coming up with a second order non-linear set of differential equations would be to say that acceleration is a first derivative of velocity, and velocity is a first derivative of position. And so we can transition this system of second order differential equations in the x, y, and z directions for many celestial bodies into a larger system of first order differential equations. That's all for now, I think, on this though. In summary, we have defined second order linear homogeneous equation, illustrated an intersection between the study of second order linear homogeneous equations in linear algebra, and described applications of linear algebra second order diff EQ and physics, including a pendulum problem, a bandpass filter problem, so an electrical engineering problem, and a solar system model. Thanks for watching.